started with our next session. So today we've got Tennessee Leeuwenburg, and they'll be presenting on PyEarthTools, machine learning for system sciences. Thanks.
Thanks, Joe. And I know it's already been done earlier this morning, but just a quick acknowledgement of country as well, just to add my support to those statements. So a little bit about me. My name's Tennessee Leeuwenburg. I've worked at the Australian Bureau of Meteorology for 22 years, mostly in the research program as a data scientist and software engineer. I'm the maintainer of two open source packages, PyEarthTools, the subject of today's conversation, and also Scores. And my main focus is the development of machine learning models for nowcasting, which is the time frame from right now out to about 3 or 4 hours. So I think for this audience we'll add a bit of a description of what actually is Earth system science, and then we'll see some examples and then kind of ease into what is the application of machine learning to that context. So Earth system science models essentially refer to modelling sort of the processes and state of our kind of natural environment, our planet, our atmosphere. And traditionally they've been process-based or rule-based systems developed by academics and researchers on the basis of physical rules. So think force equals mass times acceleration, or the effect of gravity on the atmosphere, things like that. They're amazing, but they're also very computationally expensive, which is why we have supercomputers, which we don't all have in our back pockets. So prior to 2022, the general understanding is that the complexity of that task would have greatly exceeded any feasible machine learning approach for modelling the entire system anyway. However, since then, machine learning models have come out and proved themselves very competent at the entire task. There's still a scope to what they can do, but there's really a change in the state of the field. Some of these machine learning models are entirely machine learning based, and there's no attempt to explicitly simulate the physical and chemical processes that are occurring, and it's the neural net doing what the neural net does, whereas others are hybrid, and there will be like a neural net aspect and also a rules-based aspect. And they're not all neural networks, but a lot of the big ones that are very interesting are neural networks. So let's sort of work it through with this example. So here's the example of a weather forecast. I work at the Weather Bureau. I kind of can't help making all of my examples weather. Everyone understands the weather, but the system can do a lot more than the weather, right? And there's a lot of pieces of information in here. So where do these pieces of information come from? So there's a certain amount of human value add and quality assurance to the way the Weather Bureau makes them, but behind that are these simulation models that drive the prediction of these variables. So this is an animation of a weather variable evolving around the time in a rules-based, physics-based global model. So that's an Earth system model. That's Earth system science, and what we're talking about is a neural network that can do that. So here is the code for a model that I trained that does that to a greater or lesser degree, and it produced that. So basic proof by example, that's the kind of thing we're talking about, and that's what PyEarthTools is for. It is for the construction of neural network and other machine learning based models which are capable of performing useful Earth system science simulations to the level and standard. Again, scope and caveats apply, but this isn't the deep dive on the science of them, roughly to the standard, or indeed in cases better than the standard of the physical models. So back in 2023, it was possible to actually go and find all of the machine learning models. So a colleague and I went through this process of doing so within a particular scope. So there's a lot of caveats around what is and isn't a weather and climate model and so forth, but we found the scope, and you can see in the timeline when it is that machine learning really starts sort of taking off in the field. And since 2023, there's just been an absolute explosion in the number of research, the amount of research findings in this particular field, and it would probably no longer be really reasonable to try to produce these diagrams now. But a few things from this still very much apply. So firstly, fully connected neural networks as opposed to more advanced architectures are still very much relevant in the field, particularly for very specific process problems. And also we are talking about things that don't just include neural networks. But, on the other hand, since then, a great many of the most significant results have come from the application of transformers and graph neural networks, especially to predictive models, and also diffusion models, which might be perhaps a little more focused on the problem of downscaling or super resolution, as it might be called from a more computer vision perspective. So this slide wasn't produced by me. This was produced by Andy Brown, the Director of Research at the European Centre for Medium Range Weather Forecasting. And this is where we have specific examples of these models performing to a higher standard of accuracy than the physical models. Again, for specific metrics, specific variables, various scopes and caveats apply, but they've very much held their own in terms of the headline statistics in some of these variables. So it's very much not hype, and it's very much transforming the field. So let's talk about, now that we've got that sort of scene setting out of the way, PyEarthTools itself and how it came to be and where it sits in the field and what you might like to know about it. So back in around 2022, we could see that change was on the way, and internally started work on this tool for being able to sort of deploy and run various state-of-the-art published architectures, run them against our data sets, etc. In March 2023, a framework called ClimateLearn was released. I believe that's no longer being maintained, but that's when that was released. Around the middle of 2024, a number of the Bureau's research partners, so the Met Office in the UK, NIWA, which is now Earth Sciences New Zealand, and Access NRI, which is a research group here in Australia, joined as PyEarth collaborators, and we set the intention of creating an open source framework so that we could share our work and collaborate more effectively across that partnership and with anyone else who might like to join us. In August 2024, a framework called Anemoy was released by the ECMWF. This is a very serious framework. It's got very, very compelling results coming out of the models that come from that framework. In December of that year, hot on the heels of one another, PyEarthTools was released as open source shortly after the Miles Credit framework was released, Miles Credit being by NCAR. So that's how we got where we got. And I'd just like to pause and acknowledge the PyEarthTools contributors that have gotten us to this point. In particular, Harrison Cook, who very much led the technical development of the framework for the first couple of years, and has now gone to work at the European Centre on the Anemoy framework and is now helping them in their journey. But also fully recognising and valuing the contribution of everyone else as well. And of course, it's open source, so your name could be here next year if you like. So what is PyEarthTools? So it has source code and documentation. It is a modular open source Python framework with modules for data, one line, no small task. Pipelines, so in this case, think less orchestration pipelines and scheduling, and think more declarative pipelines of the transformations that need to occur to the data. And it takes the philosophy, like a lot of models in a singular code base may closely couple the pipeline and the model itself. PyEarthTools takes the perspective that these things should be better modularized to allow more fine-grained research to occur and more reuse of standardized, scientifically validated pipelines that then data scientists can more easily just sort of pick up and work with, and each person sort of focus on their core skills they're bringing to the equation. So examples of what's in the pipeline: reprojecting, resampling, regridding, reaggregating, normalizing, denormalizing, standardizing, adding, converting units, and a great many things. And all of that ultimately turning itself into a fairly basic data structure, being a Python iterable, and then that then proceeds to the models. And then PyEarthTools also has a good number of packages and utility in it for working both with predefined models. So if there's a published architecture that have a supported implementation for, you can pipe new or different data into a predefined model architecture for people who want to focus more on the pipelines, or for people who are more focused on the modelling side of the equation, they can define their own models. If something's successful or they want to publish it, then they could put it back into the main package for wider reuse. and a certain amount of code on our roadmap coming soon for evaluation and standard scorecards for model intercomparison to support the research journey. So, to recap, PyEarthTools is for doing this kind of thing. So let's sort of pause and talk a little bit about the data. So one of the things that maybe differentiates the Earth system science world a little is that we don't need to deal with as much, say, conflicting user-generated data as if you were training an LLM, but we do have to deal with like a similarly large volume of data. So, you know, we're talking in the hundreds of terabytes to petabytes range for the largest problems, and even for the smaller problems, it's still a decent whack of data. And it has to be brought together in a great deal of differentiated formats, which are often specific to Earth system science. And I've always really wanted to kind of hide all of that behind an API. That's what you sort of have to do to get data into a machine learning model anyway. So this is a mechanism to standardize in a coded way how to do that in a way that's a bit more transferable. And these data sources are not always sort of fully documented for an ordinary user as well. Often they, you know, require a certain depth of science understanding to even actually properly unpack and process the data itself. So here's some examples of how PyEarthTools might connect data through to a machine learning model, some of the processing steps that it goes through, and we'll talk about the processing in a little more detail in a moment. But here we've got 3 separate pipeline graphs. The first one essentially just being a stick, which connects the Weatherbench 2 based Era 5 data set through the various transformations that are required. So the steps here being you need to do the dimension ordering, the variable sorting, so they'll often be like latitude, longitude, height, time. The various data sets you want to work with often have those in a different order, so there's a certain amount of just reshuffling of data that needs to occur. Certain amount of data is 0 to 360, some is minus 180 to 180. It's going to vary by not just the source, but like how the person who archived your copy of that source decided to do it at the point in time they do it, which has persisted until now. So there's a lot of pre-thinking in the PyEarthTools framework for the major sources of data and sites that we optimize for, so that sort of takes that burden off the user to some degree, and they can use a pre-named pipeline to sort of, you know, get a bit of a head start on working with the data. Temporal retrieval to turn it into the appropriate sort of sequence-to-sequence pattern that we're talking about, because there's a history to the training, the prior examples, but then there's a number of sequences that you want to generate in your forecast period of lead time as well. So that sort of reshapes the data for presentation to the network. Convert it to NumPy, play with the dimensionality a bit more, work out the Z-scaling standard deviation, cache it, because that was a lot of work, and then be ready to start, you know, running epochs over the data. And on the top right, we have a similar example, but in this case, we're trying to, this is utilizing to produce the El Nino index out of, you know, so the right-hand side goes down to a single value, which is that index value, but on the left, we're preserving latitude and longitude dimensionality in the input data. So a lot of this sort of pipeline stuff is around how to handle appropriate data transformations, and it's the source of a lot of mistakes. So, like a recent example is someone was working with hail data, lightning data. Lightning strikes are relatively sparse. They were preserving latitude and longitude when calculating their normalization factors. There were a lot of missing data and NaN values, and so, you know, they hadn't plotted it. They weren't aware of it. These sorts of things allow the scientists involved to get in there and do things like inspect normalization weights and understand data representations. Quick plot, quickly identify the issue. Let's just collapse it to a single standard deviation rather than something that's spatially varying. Happy days. So what are the strengths of PyEarthTools? So we do take into account the hardware consideration. So running one of the global scale physical models is not something you can do on an ordinary laptop or computer. Running a global machine learning neural network based weather model is something you can do on your own laptop or computer for many laptops and computers. Training them is something you might need a very high-powered GPU for. More, it's the data. The data volumes are very prohibitive. But training a low-resolution one is not prohibitive and can be done, and we've got that in our tutorials, things that you can do for yourself. So one of the advantages, I think, is this can put, from a learning perspective, the ability to work with real-world science into a more consumer class of hardware or more commonly available source of hardware and category that people are going to be able to do more experimentation with. So it's been run on laptops, workstations, and supercomputers. It supports standardization and repeatability. It has lots of documentation, and it's a forever job to make it as good as it can be, but we're very much on that journey. And it's independent with respect to the machine learning architectures. So it can work with any machine learning architecture or framework. So the three that we've integrated it with thus far in the tutorial examples would be XGBoost, PyTorch, and the Apple MLX framework. But it will function, very happily together with JAX or TensorFlow or any other one that you might care to add. So that's also a feature, and that's why to separate the pipelines from the models, because the feed of the pipeline is something that's typically going to be NumPy based or a simple array based. It's very numerical. Having that as something that can be done in a standardized sort of X-array open source stack, separate from the model itself, allows you to be more modular and objective with regards to your choice of actual neural network stack. So when I say network here, I mean neural network, not network cable network. So what are the motivations for continuing to do PyEarthTools, and why is it of interest for others? So much of machine learning research in Earth system science uses a custom stack. So there's sort of a few categories. Like there's Anemoy, which has a particular family of models in it, and it's probably fair to say it's best of breed for that particular family and class of problems. But there are equally as many amazing models that are built in pure PyTorch or pure TensorFlow or pure JAX that don't connect particularly to one another. So PyEarthTools, we aim to be able to bundle more model architectures, give people a leg up, give people predefined architectures, give them a starting point, unburden some of the interface into the supercomputing facility and the complexity of the data sources, and move a bit closer towards modular reproducible science. So that's sort of the purpose. It's accessible by being, it's on PyPI, it's on GitHub, you can just get it, there's no overheads or barriers, and it will work on your computer. Flipping the equation, it allows you to document and share your workflow back with the community effectively. So if people choose to adopt the framework, they're going to be able to collaborate with their partners on model versions and model upgrades and differentiation and pipeline versions more effectively than if they were gathered around specific models. So that's the basic principle. And it gives people just a way to give back as well, which is also a motivation for many. So let's look at some things that you can do for yourself. So we have 4 specific tutorials which are focused on requiring no more than a 4 gigabyte GPU and an amount of data that you can reasonably just download over the network in real time. So the data volumes here top out at kind of 10 gigabytes. Maybe you don't even need more than 3, and many workstations and laptops would be able to do not just the inference, but the training. So the emphasis here is very much on putting the ability to train back into the hands of as many people as possible with as few barriers to entry as possible. Pardon me. And we have a long and interesting tutorial gallery full of lots of worked examples. It's very easy to get involved. So community engagement and community contributions are warmly welcomed. I'll be here for the sprints, so please do consider coming along to the Pycon AU sprints, and there'll be some other developers online who can help orient you and get you started as well. Run through the tutorials, and there's a few other ideas, and if you just want to keep in touch with PyEarthTools and see what's going on, the Access NRI Machine Learning for Climate and Weather Working Group is the place where most of the conversation about the ongoing development of PyEarthTools is occurring at the moment. In terms of our roadmap, Really, the next major objective is adding standardized scorecards so that we can do far more straightforward model intercomparison between the different architectures. And so that, again, students or people starting new projects or early career people have ready access to see how what they've trained stacks up against, baseline stats from other models. Add a further range of benchmark model implementations for more classes of problems so that the framework is open and of interest to more different researchers from different backgrounds on different problems. Bundling more kind of basic model archetypes. So to me, the difference between an archetype and an architecture is like this particular network with this particular depth and this particular size and this many layers, so a lot of the choices are made, whereas an archetype is like a graph neural network, a CNN, etc. So that we've got more worked examples for some of the intervening steps between starting, a blank sheet of paper and a functioning model. And as always, a bit of refactoring and simplification. So I'm not quite sure where that leaves us for time, but that has run me out of slides. Can I get a quick time check? 10 minutes. Well, I think that's the goal, isn't it? Great. So we can stop there for questions, and if people don't have any questions, I can fire up tutorials if I can get the network working.
Thank you, Tennessee. That was a really awesome talk. It sounds like a really neat tool. So do we have any questions?
Hello. First off, thank you. Great talk. So I'm a platform engineering person, so I'm wondering if there's any way you could say something about how this is being made available and how that's hosted for analysts and researchers to consume within the Bureau.
Sure. So, in any particular, you'll have to find someone to install it in any particular organisational context. The main use of this by the Bureau and the community is in research facilities that are for that particular purpose, because of most of the focus being on training and reproducibility at this stage. There is, I think very wisely, a lot of scrutiny being put on these before they would go behind any kind of production service, and frankly we're not there yet. So it's more, so the emphasis is on the optimization at NCI. There's a pre-built what's called a modules environment, which is, that would be of use to, that's fairly generally open. I don't know exactly how open, but if you're a researcher in the field, I don't see why you wouldn't be able to access it there. But it's also pretty straightforward to pip install. Like, there's a lot of packages, but other than there being a lot of packages, like I run it on my machine. Most of the developers run it on both their facility and an individual instance on a laptop as well. It doesn't require much. So it's Python processes kind of beginning to end, a bit of Dask, a bit of PyTorch. You don't need like an ML flow server or this server or a database server or anything like that. It can kind of go where you want to take it.
Hey, just interested in a sort of a deep dive into the actual models and the machine learning side of that. Right at the start, you sort of talked about you showed a very dense slide of code that was machine learning version of a particular model, and I'm wondering, what are the data scientists and the data modelers learning from the machine learning that is kind of producing a synthesis of those ideas?
Yeah, that's a great question. I don't know whether this dense slide, it stopped sharing. The dense slide full of code is going to help an enormous amount. What people are learning is that the machine learning models, they had a lot of, let me reframe it in terms of the questions they're asking, okay? So one of the questions they were asking are, do they fail different or do they fail the same? Do we have things like model collapse occurring? Are they effective outside of the training envelope? How do they handle rare and extreme events? How do they work in terms of the probabilities of those events occurring? And those are questions which are kind of natural to ask from a scientific perspective. And so a lot of what they're doing is, like, you might look at I'm going to get the words on the tip of my tongue, but essentially the spatial sensitivity map of the model to the data. So they're looking to find physical regions that they can understand as a scientist, which are influencing and resulting in those model predictions. So, and whether the probability curve, so most physical modelling now is what they call ensemble modelling. So there's an increasing emphasis not so much on going, there will be exactly 20 degrees of temperature, and more the odds of exceedance of a variety of thresholds is such and such and such. And they do that at the moment through a kind of initialization process with carefully managed noise of a fleet of ensemble members. And they're reconsidering how to do that in the light of things like a diffusion process, which is more like a Gaussian noise model and less like a physical noise model. And so there's a lot of interplay between, like, as the physicists with those deep and modelers of that sort of deep physical understanding are framing their understanding of the machine learning models to try to produce those similar outcomes. At some level, what they're finding is that the machine learning models have quite similar strengths and weaknesses to the physical models. They're trained against something called reanalysis. A reanalysis is a mixture of observations, but away from the observations, it's model data. So it's a modelled estimate in the sparse, to fill in the sparse data. So to some degree, the models are trained on emulating a physical model. There's a really interesting line of research on direct from observations training, which I think is really, that a lot of the focus of the cutting edge is really moving into direct from observations. That definitely gets me out of bed in the morning. That's super exciting. So I'm not entirely sure if I just tried to give you a flavour. Yeah, good play.
Thank you, Tennessee. Great presentation. Just in the background of this package, all the weather variables are built into that, so we don't need to know where they come from. And my question goes to, can we use things like that output you showed, that 3 to 4, say, wind, we could do a wind forecast. Can we use that then with other products to, say, do fire modelling in the short term? We've got a bushfire. We then model what the wind's happening with some topographic effects. Can we predict that fire? Is that the intent for a package like this?
Yeah, that's certainly the intent. So let's talk about this, can we do it? Like, not in production today, right now, in easy grasp. In principle, using machine learning with a data-driven approach in research, yes, definitely. So the intent there is to provide, and the focus again is still on training. So in a production setting, you've got a whole IT architecture to consider. In a research setting, it's like, can we make the models to do that job effectively? And I'm very interested in things like whether we can take like a good foundation weather model and then add a field from another discipline or area, such as fire spread or some other well-stored data set, and then learn those relationships without having to do the full retrain. Up until now, as you can see, since it's only just a small amount of time that those models have gone from kind of close parity to the atmospheric model to genuinely competitive atmospheric modelling. I think that's sort of, we're on the cusp of all of those sorts of changes. And if you're interested, tap me and I'll send you a bunch of links. Yeah.
Okay, really quick question.
This might be tangential to PyEarthTools, but have machine learning models been used to characterise the statistical distribution and spread of weather ensembles models in terms of trying to optimise the number of ensemble members and things like that?
Not in terms of optimising physical ensemble members. In a lot of ways, the machine learning has happened so quickly, the physical modelers have only barely had time to react to this change in the field. So they'll try to work out how many machine learning ensemble members to run, but they're quite cheap to run. So you can more or less run just as many as you want. So there's not the same kind of constraint. And people haven't really sought to back connect to the physical modelling world. There are lots of reasons to maybe do that, like guardrails, explainability, fallbacks, etc. But yeah, interesting times.
Cool. Can everyone thank Tennessee again? And we've got a mug for you.
Thanks very much.